So we're trying to investigate how the resistance of a resistor varies with temperature. So we're going to need some way to vary the temperature of the resistor. So a water bath over a Bunsen burner or a electric hot plate, a thermometer to keep track of the temperature, an ohm meter to measure resistance, and glycerol or oil or water bath for the resistor itself. So as always, don't forget your units, don't forget to label your axes, make it nice and big. I've put the resistance in the y-axis, temperature in the x-axis, because the temperatures are independent variable which we're manipulating to see what how the resistance changes, which is our dependent variable on the y-axis. So plot a nice smooth curve. I get an answer of 33 degrees for the 1.6 kilo ohms reading, but anywhere between 30 and 35 is acceptable. 32 is on the money. The other things, how does the resistance of the resistor vary with temperature? As you can see, as the temperature increases, the resistance decreases. And what's the general name given to this type of resistor? It's a thermistor. Okay, here's the apparatus we're going to need for this experiment. A tuning fork, the resonance tube with the way of altering the length of it, the length of the air column inside, by submerging it in water to a lesser or greater extent. A meter ruler for measuring the length of the column, something to measure the inside diameter of the tube, a vernier caliper, and the tuning fork itself. Okay, before cracking on to this actual question, I just want to go through a little bit of this because it might have been a while since you've covered it. So pictured here is just the inside of the tube, and all those little dots are meant to represent the particles of air. So let's try to get an idea of what happens as the sound wave propagates down the tube. So it's a longitudinal wave, and the particles are going to oscillate back and forth in the same direction that the wave is propagating. So they're going to kind of go back and forth in the same direction the wave is moving. Focusing on what happens at the bottom of the tube, you've got that sound wave moving down the tube, pushing the air particles, oscillating back and forth in the direction of down the tube. But when you get to the bottom, you've also got the sound wave rebounding back again. And at that point, the waves cancel each other out with destructive interference. As you move further away from the bottom of the tube, you're going back towards the top, you're going to get less and less destructive interference. At this point, just to help kind of picture what's happening in a little bit more detail, we've drawn the sound wave, even though it's not a transverse wave, we've just drawn it as a transverse wave as a way of picturing what happens. It's much more easy to visualize. So, and as you can see, the maximum amplitude, the maximum displacement is at the very top of the tube. So at the bottom we had destructive interference, and at the top we're going to have constructive interference, and the wave's at its strongest. So the top of the tube, where the resonance is occurring, isn't one full wavelength. In fact, it's not even a half a wavelength. It's actually a quarter. If you can follow this in the tube, that solid green line is the only portion of the wave that's in the tube. The rest is outside. And if just remember that little green semicircle to the right there they've indicated, that's only half a wave. So pictured there, that will be one full wave to the side. And one full wave is one full wavelength, obviously enough. The points of a wave where there's no displacement occurring, they're called the nodes. And the points where the maximum displacement is occurring are called the antinodes. And just a quick reminder here, sound is a longitudinal wave. We've just drawn this transverse so we can see what's happening, but the behavior is the same regardless of the type of wave. So as a repeating pattern, there's a node every half wavelength, and also there's an antinode every half wavelength as well. But whereas the nodes start off at the 0 point, so it's like 0 wavelengths, half a wavelength, one full wavelength, the antinodes start off at the quarter wavelength position. So quarter, then 3/4, then 1 1/4, then 1 3/4, and so on. Okay, so I've taken a bit of a waffly journey around all things wave related, and I've just noticed now I've made a mistake here. See where it says node at the top? Now we should know better, that's an antinode. I just had a brain freeze. Okay, so why have we been going on about this? Let's go back to our tube. The length of the tube L is where we go from a node down the bottom to an antinode up the top of the tube. And we said that antinode will happen at a quarter of a wavelength. So the length of the tube is equal to a quarter of a wavelength-ish. Well, almost. There's one slight complication. The actual antinode, again, why didn't I fix it? Anyway, the actual antinode is a little bit above the top of the tube, just a tiny bit, and we just have to take that into account. So the actual antinode, where the resonance is happening, is a tiny bit above the length of the tube. It's 0.3 diameters above the height of the tube. So finally, we've gotten that the length of the tube is pretty much a quarter of a wavelength, but it's actually a little bit less. So the length of the tube plus 0.3 of the diameter is a quarter of the wavelength of the harmonic wave. Okay, so all of that was really just a bit of background to remind you of how waves worked and what we kind of need. Let's get back to the actual question. So they're trying to find out the speed of sound by using this apparatus. So let's go back a second to when you're covering waves. Wave speed given by the wavelength times the frequency. And we just determined for this setup that the length of the tube plus 0.3 times the diameter will give us a quarter of a wavelength. So rearranging that just to be in terms of the wavelength, you have 4 times, in brackets, the length plus 0.3 times the diameter will give you the wavelength of the wave. Multiplying both sides of that equation by f for frequency gives us 4 times the frequency, and then in brackets, the length of the tube plus 0.3 times the decimal is equal to the frequency times the wavelength, aka the speed of the wave, in this case the speed of sound. So the speed of the sound is 4 times the frequency times in brackets the length plus 0.3 times the diameter. Okay, so now we have a starting point for figuring out the speed of sound based on the experimental data in the question. So subbing in the experimental results for the first run, for the 512 Hz tuning fork, the length of the tube is 153 millimeters, and the diameter of the tube doesn't change, it's always 35. So 35 by 10 to the minus 3, because remember to convert this into meters, and it works out as being 335 meters per second. Then plug in the numbers for the second 2 trial runs and do an average, and it works out as 340 meters per second. Okay, so finally they want us to find out the length between 2 resonances, between the second and third resonance for this wave. So this person's going to extend the tube until they get to that point. And going back to our wave representation here, the first resonance was at the top of the tube in its original position, and now they've extended the tube until you get to the next resonance, which is when the amplitude is at its greatest. And like we were saying, this happens every half a wavelength, so the quarter wavelength point and then 3/4. And this will be the same length no matter which resonance we're talking about. It's always going to be half a wavelength in the difference. So a slight rearrangement of the wave speed equation gives us the wavelength in terms of the speed divided by frequency. So this time run off your average that you've calculated. I could understand if you ran off the individual result you got for the 512 one, but I always go off the average, and it works out as 0.66 meters is the wavelength. And don't forget, we're looking for the distance between the 2 resonances, which you said was half of that wavelength, so 0.33 meters.